what do you need to know about a Turing machine is going to be on the Turing defined a model of computation. All right. And what is it there? That's a Turing machine. All right. So I flash up a picture. That's a Turing machine. It has a bunch of states. It has a tape. All right. That's it. There. Everything you need to know about a Turing machine is that it computes, right? We assume that it's given a binary string as input that's on the tape, and it computes, and what you get is an answer, right? So here we're saying P is computable. There exists a Turing machine that on all inputs, the Turing machine runs and it gives you the right answer for the problem, right? That's what we've been saying all along, right? Everybody understands this? This says P, right? So then what does Turing say? Turing, this here is a set of computational problems, right? This is, if the problem is inside here, it's computable. If it's outside, it's not computable, right? Here the problem, the halting problem is outside and sorting's inside, right? To be inside, this is the definition of computable, that there exists a Turing machine that solves it for every input. That's what computable means, right? Now, it's equivalent to saying a Java program can solve it, right? So this says there exists a Java program that are on all inputs. It solves the problem, right? Here, this is saying it's computable by a Turing machine. This is saying it's computable by a Java program, right? Everybody understand that? So now you know everything about Turing machines that you need to know for this test, for this course, right? All you need to know is Turing machines compute, right? That's what you need to know. All right. So this, now we're going to say if a Turing machine can do it, a Java program can do it. If a Java program can do it, a Turing machine can do it, right? We're showing that they're equivalent. It's like saying if a boy can do it, a girl can do it better, right? If a Turing machine can do it, then a Java program can simulate it, right? Similarly, if a Java program can do it, then a Turing machine can do it, right? Does that make sense? Right? So,
and I was gonna say, yeah, and also not to mention that, yeah, Turing machines are also automatas are also used to like model the Turing, the computation of the Turing machine.
yeah,
so,
but we don't need to know any of that. If you start talking about the details of a Turing machine, then people are going to panic, right?
Okay. Enough of that. Yeah.
Save it for 2001. Right?
Unfortunately, I'm not in your section for 2001, but I'm just bringing it.
Yeah.
I thought I'd bring it up for a bit, but yeah. So.
All right. So now what also matters here, that's my father and this is me. What also matters is running time, right? So this could be the set of all computational problems that are solvable in poly time. This is the set of ones that can solve in exponential time. This is the ones that can be computed at all, right? And why are they inside each other? Well, because if you can solve it in poly time, then you can solve it in exponential time, right? Because exponentials are bigger. And if you can solve in exponential time, then you can solve it, because here you're allowed any amount of time, right? So that's why they're nested like that. All right. So here we're bringing in the idea of time, right?
So
and yeah,
kind of related. Just yes, like I think it's yes or no. Is this kind of related to DFA and regular language classes?
Yeah, you just guys move away from 2001. Move away from it.
Okay.
Right? DFAs live down here. They're inside linear time. Right? Here we're just saying, can it be sorting can be solved in n squared time, right? But how to play chess that takes exponential time, right? The halting problem can't be solved at all, right? Everybody good? So what's key here? We're stressing it again. What's key is that the machine must be fixed and known before we know the input, right? I'm just reminding people of what the game is. What are we saying? Is there exists one fixed machine that works for every input, right? And then the running time, right? So here we're using coding phase. Remember before we used compile time, right? Now I'm using coding phase. During the coding phase, you have to come up with the machine, the algorithm, right? Before you know the input. And during the execution phase, I used to call it running time. During the execution phase, you get to determine how much time is needed, right? And that happens after the input, right? And what does sentence A say, right? We want to translate sentence A. Sentence A says, computational problem P is computable by a Java program, right? Everybody agree that's what A says? What does A say? It says there's some Java program that on all inputs, it can compute it with some amount of running time, right?
Sorry, is it running time or execution phase now? Because I'm a little bit confused.
All right, so the reason we switched it is because running time had two different meanings, all right? So what the two meanings are is now we have execution. Let's forget that this was running. There's a period of time after the input is come up with, and I did call that running time, but now I'm calling it execution phase, right? So execution phase is the period of time after we come up with the input. But what's running time? Running time is the length of time it takes for the algorithm to run. Are you there?
Oh, yeah. Sorry, I didn't realize I was mute. Yeah, I get it now. Thank you.
All right. All right. So now what is this saying? Right? So what does Z say? Z says the computational problem is computed by a Turing machine. Right? Everybody understand line A and line Z? Right? All right. What are we going to try to prove? We want to prove that if A is true and a bunch of things that are useful are true, then Z will be true. We're trying to prove that if a computational problem is true for a Java program, then a computational problem will be true for a Turing machine, right? In fact, Simca, am I saying that right? Simac. Anyway, here, look at P is a free variable, right? And if P is computable, then A is true and Z's true, right? And if P is not computable, uncomputable, then A is false and Z's false, right? So, but what is true for any P, if this is true, then this is true. All right, everybody with us so far? All right, let's go on to see what things do we need to add in here, right? What we need to add is a line that says, hey, Java programs can be simulated by Turing machines, right? If we want to go from the fact that a Java program can do it to the fact that a Turing machine can do it, then what do we need to know? We need to know that any Java program can be simulated by a Turing machine. Right? Everybody buy that we need to know that? And here we can also say in the simulation Do they use the same amount of time? No. Well, maybe the Turing machine takes the square of the amount of time that the Java uses. If the Java uses t time, then the Turing machine uses t squared time. Right? Does that make sense? We're going to write down a first order logic statement that says this. Right? Then what's B going to say? B says computational problems. Look at here, you might not have noticed this. Here, the input to the Turing machine is in binary, and the input to the Java program is in ASCII, right? So they're taking, problem P is taking on completely different inputs, right? Here it's taking a binary string, here it's taking an ASCII string. And what does B say? Computational problem doesn't care whether the input's in binary or in ASCII. Computational problem will treat the two the same, right? Does that make sense? So what do we have to do left? We have to formally state B as a first order logic statement. We're going to state C as a first order logic statement. And then we're going to use the oracle. Oracle is going to believe that A is true and B is true and C is true, right? And if we have an oracle that gives us A, B, and C, then we're going to play the game to prove Z, right? And if you're American, we're going to prove Z. But American has Trump, so let's not prove Z. Let's prove Z. Everybody good? All right. So let's go on and think about the difference between binary and ASCII, right? You might not have known the difference between binary and ASCII. So let's look at that. That is a binary string, right? It's a string of zeros and ones. And we can have a compiler or a function, a translator, that takes this binary string and it output ASCII string, right? If you don't know what ASCII is, it's American something. I don't know what it stands for, but it's the code, which the way we type letters. ASCII means letters and numbers as you know it, right? So here's an ASCII string, hello world. Here's a binary string. And you can all imagine that there's a way to convert this into this. In fact, there's a table that tells you what binary string is in H, what binary string is in E, right? Everybody good with that? So what do we want our B to say? We want to say, hey, there's some function B that maps binary inputs into ASCII inputs, right? We want to say that there exists some mapping, right? And so here we're just saying, here, B is some function that you give it a binary, it gives you an ASCII. In orange, I don't know if this is orange or brown, but in orange, the I prime is in binary, and the I is an ASCII, right? So what does B do? Is it takes as input the I prime, and it outputs an I, right? And they're color coordinated to help us remember where they're coming from, right? ASCII and I come from this yellow sentence A, while binary and I prime come from the sentence about Turing machines, right? And B comes from our blue sentence, right? So everything's coordinated, color coordinated, so we know where it comes from. So what do we want to say? We want to say that this computational problem doesn't care whether you give it binary or ASCII, right? So the computational problem treats them the same, right? So here we're going to say the required output of computational problem P when you give it a binary string and when you give it the equivalent ASCII string, the computational problem is going to require you to give the same answer, right? Now for which inputs? For all inputs, right? This is saying you give me any binary input. I can take that binary input and I can translate it into an ASCII input. and the computational problem will require the same answer. Right? Does that make sense? Are people understanding B?
Can you explain it again? I don't get B.
All right. So let's go from the we're going to go through it more in a minute. So, but just for now, let's say what we're saying is that computational P treats all inputs the same, right? So you give me any binary input and you say, what does computational P, what answer does it require on input I, right? Let's say P is sorting, right? What's the input to sorting? Well, it's a bunch of numbers. I could give you those numbers in binary, and what does P require? It requires that you sort those binary numbers, right? Or I could give you the same numbers as in 1, 2, 3 in ASCII. And what does the sorting problem require? It requires that you sort the numbers. And I don't care whether you give it in binary and ASCII, it's the same problem.
So it's just saying that the binary and the ASCII are the same thing.
Are
Just-
treated the same,
Okay.
right? So now M is a Turing machine. No, sorry, M is a Java program, right? M is a Java program, and we put it in this. There's a compiler where you put in a Java program, and out comes a Turing machine, right? And more or less, if you've taken 2001 from me, then you've done this. I give you on the test something that looks kind of like Java, a Turing machine. So on the 2001 test, I gave you code that did insertion sort, and they wrote me a Turing machine that solves insertion sort, right? Now, are we going to do that compiling? No, that's for 2001, right? But you do have to understand that, you can imagine that there exists a compiler that you give me Java code and I give you a description of a Turing machine, right? You can imagine that such a thing exists, right? So what will our statement say, right? Our statement says that here we have a compiler that translates Java code into machine code, right? So what we're saying is Java programs can be simulated by Turing machines, right? And what do we need? Let's build it up. What we need to say is Java programs can be simulated by Turing machines. Well, which Java program? Which Java program can be simulated by a Turing machine, right? Here we're saying Java program M can be simulated by a Turing machine, right? I want to know which one. Oh, it's M that can be simulated by a Turing machine, but which is M, right? We need the fact that, what do we say? Are we saying every Java program can be simulated by a Turing machine? Or there exists a Java program that can be simulated by a Turing machine, right? We want to say every Java program, right? Every Java program can be simulated by a Turing machine, right? So now, what do we mean by simulated by a Turing machine? What do we mean by that? What does simulated mean? It means that there's a Turing machine. Here, the Turing machine is in orange, right? M prime is our Turing machine. And we know that Turing machine, what does it mean for Turing machine M prime to simulate Java program? It means that the two programs give the same answer, right? This Java program and this Turing machine give the same answer, all right? All right, well, which Turing machine are we talking about, right? Are we talking about every Turing machine gives the same answer? No, we're not saying every Turing machine gives the same answer. We're saying there exists a Turing machine that gives the same answer. For every Java program, there exists a Turing machine that gives the same answer, right? All right, well, here they give the same answer. What are we missing?
Time.
What?
Time.
Time. We're missing time, and we're missing something else.
Computable, like if it's computable or not.
Yeah, well, here, yeah. That's certainly, here we don't, no. It's not whether it's computable because there's no computational problem here, right? We're not going to mention P here. We're mentioning Java programs and Turing machines. There's no computational problem here, right? So what haven't we mentioned?
Binary changing.
Yeah,
Imports.
the input, right? Java, the Turing machine and the Java program, they give the same answer given the corresponding inputs, right? One is giving a binary string, one's given an ASCII string, but when you give them the corresponding inputs, they give the right answer, all right? So for what input does it do this? Does it do it for some inputs? No, it's got to do it. It's got to do it for every input, right? For every input, it's got to give the Turing machine, for every input, this Turing machine has to give the same answer as the Java program, right? People following that? And so here, so what are we saying? What's the corresponding inputs? Well, we're going back to, you give me some binary input, and I can translate it into an ASCII input, right? All right, so that's why we're saying the input, we're given the I prime, right? For every I prime, for anything that the Turing machine could be given, right? We're saying anything the Turing machine could be given, it's going to do the same thing as the Java program will do on the corresponding input. All right. So how do we denote this? We say that here's given an arbitrary binary input, the Turing machine on its input does the same as the Java program does on its input. Right? Does that make sense? All right, so now we want to write down the whole sentence, right? Let's make sure we understand this sentence. People wanted more examples, right? This is another example. I'm not bringing in crazy, what is a Turing machine? This is just a reasonable example, right? This says, given any Java program, right? The adversary gives me any Java program whatsoever, right? I can come up with a Turing machine that simulates it, right? And what does simulate it mean? Now we have a Java program and we have a Turing machine. What does it mean for this Turing machine to simulate this Java program? It means you give me any binary input that might be given to this Java Turing machine, right? You give me any binary input. I take the binary input and I translate it into an ASCII input, right? Then what the Turing machine does on the binary input is exactly the same as what the Java program does on the ASCII input, right? Does that make sense?
Yeah, sorry, I just wanted to mention that it's 12:55, so we have 5 minutes.
All right, exactly. And we can, let's just mention running time and then we'll stop, right? Yeah, I must admit, what we did, I thought we were going to finish all these slides last class, and instead we're going to take 3 classes to do it. But that's okay, as long as we get it, right? Guys, study at home by yourself, because I want you to get this, but we do have to get through this material, all right? So now let's talk about running time, right? We're going to also say that the Turing machine takes the square of whatever time the Java program takes, right? So here we have the Turing machine, we have the Java program and the Turing machine already. And what we're saying is we're going to say Turing machine M prime takes the square of whatever M takes. So how much time are we talking? Well, if the Java program takes M time, then the Turing machine takes it. Sorry, if the Java program takes T time, then the Turing machine takes T squared time, right? For which time? For some time, for any time T. If the Java program takes T time, then the Turing machine takes T squared time. All right? So what we say, right? We want to say for any T. This is true for any T. You give me some T, right? And we already have the input, right? We have the Java program, we have the machine, we have the input. And if it's the case that the Turing machine, if it's the case that the Java program takes T time, then it's the case that the Turing machine takes T squared time, right? And that's actually true. Going from a Java program to a Turing machine, there's a blow up of squaring the time. All right. So here, what we're going to do next class, right? We've stated that Java program can solve the problem. We've stated that, right? We've stated these three things, and we're going to formally prove that if A, B, and C are true, then Z is true, right? Everybody got that? All right, let's finish for today.